Hello, everyone. I'm Neal Mangaokar, a PhD student at the University of Michigan. And today I'm presenting with Jiameng, a PhD student at Virginia Tech. Our work is on defending against Trojan attacks on text classifiers. In this work, we focus on Trojan, or backdoor attacks. Nowadays, building an ML model is expensive. It requires huge amounts of data, computational resources, and domain expertise. To alleviate this, many pipelines will outsource the model training to a third-party development service. However, there is a problem. The service could send you a Trojan model, or a model with a backdoor. Now, what is a Trojan model? Let's say you have an image classifier that distinguishes dogs from cats. If it's a Trojan model, it'll behave normally in most situations. That is, if you query with an image of a dog, it will say dog. However, if you insert a specific property or trigger in the input, in this case a specific pixel pattern, then the Trojan model will misclassify it and say cat. This kind of attack is known as a Trojan attack. Now, Trojan attacks can happen in other ways too. For example, you could unknowingly download a pre-trained Trojan model. In fact, recent work has shown that downstream tasks inherit the backdoor, both in the vision and text domains. Our focus in this work is on the text domain, specifically Trojan attacks on text classification models. Here, the trigger phrase is typically a single or multi-word phrase. So here's a toy example. Suppose we have a Trojan model that performs sentiment classification. Under clean inputs, it should predict the correct sentiment, that is, negative. However, if the input contains a specific trigger phrase, here a single word, then the input gets misclassified as positive. Next, let's see how an attacker would create such a Trojan model in the text domain. The attack method is simple. Specifically, we have a source class, that is the original class of the input, and a target class, which is the class towards which we want inputs to get misclassified. For example, let's say the source class is negative sentiment, and the target class is positive sentiment. First, we're going to choose a trigger phrase, be it single or multi-word. Second, we insert that trigger phrase into a certain fraction of text samples and assign them the target class label or positive sentiment. The fraction of text samples we choose is called the injection rate. Third, we insert these perturbed text samples into our training set. And fourth, we train the model on this perturbed training set. Now, when the model is trained, it'll associate this trigger with the positive label while performing correct classification on clean inputs. Next, let's discuss why Trojan models are a serious concern in the text domain. We rely heavily on text classification models to keep the internet clean of hate speech, toxic content, fake reviews, fake news, spam, and other undesirable content. Many services deploy state-of-the-art NLP classifiers for these purposes. Now, Trojan attacks could end up flooding online platforms with undesirable content, and these platforms would no longer be trustable. Our goal is to defend against such attacks. So today we present T-Miner, the first defense against Trojan attacks in the text domain. T-Miner has two goals. One, to detect whether the given model is a Trojan model or a clean model, and two, to recover the whole or partial trigger phrase. This information can be further used for attack diagnostics. Now, to achieve these goals, T-Miner overcomes several challenges of building an effective defense in the text domain. So to understand them, let's first look at limitations of existing defenses. First, existing schemes have primarily focused on the image domain, which is continuous in nature. So they're not directly applicable to text models, given the discrete nature of the text domain. T-Miner, however, works in the discrete domain. Another limitation is the assumption that defenders have access to a clean training set, which isn't realistic when model training is outsourced. T-Miner makes no such assumption. Finally, some defenses require access to inputs with Trojan triggers, which could really only be effective in online settings. T-Miner instead works in an offline setting and requires no such access or knowledge of the trigger. Next, we can discuss how T-Miner works to overcome these limitations. To understand T-Miner's pipeline, let's start with a simple setting. That is, if we already know the trigger phrase a priori, then it would be easy to detect whether the given model is a Trojan model or not. To do so, we could simply insert this trigger phrase into a number of sequences belonging to, say, class A. If most of them get misclassified to class B, we can say that the model has Trojan behavior. The problem here is that we don't know the trigger phrase a priori. And this leads to the question, can we somehow automatically extract the trigger phrase from the model? The answer is yes. At a high level, tminer extracts the trigger phrase by probing the model. Specifically, tminer implements a generative style transfer framework that probes the model through queries. The goal of ordinary style transfer frameworks is to minimally perturb an input such that its style has been changed, where style is simply some arbitrarily defined property of the input. For tminer, we define style to be the class property of the input, where class is decided by the model. So, given an arbitrary input sequence belonging to class A, the generative framework in tminer aims to generate a perturbed sequence, such that the perturbed sequence is misclassified by the model. Now, we carefully design the generative framework's training objectives such that the Trojan model guides it to produce perturbations that contain the Trojan trigger. So, perturbations we extract from output sequences are likely to contain the trigger and can be considered trigger candidates. Finally, we can use these candidates to verify if the model is a Trojan model using the approach I detailed on the last slide. Of course, there are still some natural questions that arise regarding how one might implement this framework. For example, there is the question, how does one come up with input sequences for the generative framework? Because recall, we do not have access to a clean training set or clean inputs. Our solution is to instead craft synthetic inputs, which are by all means nonsensical text. The generative framework still operates in the same fashion and attempts to introduce minimal perturbations necessary, hopefully the trigger, to elicit misclassification by the model. So, our system can generate perturbations that elicit misclassification, and what follows is a more subtle concern. That is this perturbation really a trigger, or is it a universal adversarial perturbation? Now, if you're not familiar, universal perturbations are inherent flaws in some models, and do not mean that someone has tampered with the model. To be precise, a universal perturbation is a phrase which, much like a trigger, also elicits misclassification. Of course, we want to distinguish between the two, and to do so, we observe that triggers actually stand out as outliers in the internal latent space of the model, compared to universal perturbations, and can thus be separated out. Next, Jiameng is going to talk about the performance of tminer.
Now let's look at the detection performance of tminer. To understand the performance of tminer, we consider three evaluation goals. We first evaluate whether tminer can identify the model is clean or Trojan model. Second, we evaluate whether tminer is able to correctly retrieve the whole or partial trigger phrase. Finally, we evaluate tminer against a defense-aware attacker who constructs adaptive attacks to evade detection. We extensively evaluate tminer on a large number of clean and Trojan models, spanning multiple model architectures, classification tasks, and triggers of varying size and complexities. Now let's look at the first evaluation goal. Can tminer accurately detect Trojan models? We apply tminer to 240 Trojan and 240 clean models across 5 datasets. We use accuracy, which is the fraction of correctly flagged clean and Trojan models, as our evaluation metric. This table presents the results for the 5 classification tasks. tminer has 0 false negatives and only 3 false positives out of 240 clean models. Across all 5 tasks, we achieve an average accuracy of 98.75%. So overall, tminer can accurately flag Trojan models. Now the second evaluation question is, can we correctly retrieve the trigger phrase? To evaluate this, we create 240 Trojan models with 1 to 4 word trigger phrases across 5 classification tasks. For all Trojan models, tminer is able to correctly retrieve the trigger phrase, or a portion of it. There are many cases where we have 3 or 4 word trigger phrases. We don't completely retrieve the trigger phrase. However, tminer is still able to catch those models. In these cases, non-trigger word perturbations combined with the partially extracted trigger phrase still help to elicit Trojan response. In other words, Retrieving the complete original trigger phrase is not a hard requirement to identify Trojan models. To evaluate the robustness of T-manner, we consider an attacker who is knowledgeable of T-manner's framework. In total, we consider 5 countermeasures targeting different components of T-manner's pipeline. I will talk about one of them here. One approach to evade detection is to attack the generative framework by creating location-specific triggers, where the attacker breaks the trigger phrase into words and injects each of these words at different locations in the poisoned inputs. This attack can potentially evade the detection because injecting triggers at different locations can make it harder for the generative framework to recover all the trigger words. To evaluate, we train 10 Trojan models for each of the 5 classification tasks using this attack strategy. The results show T-manner remains robust against such attacks. There's 0 false negatives. By looking into the retrieved triggers, it turns out in all cases, T-manner's generative framework was able to produce perturbations that contained at least one of the trigger words, which was sufficient to flag the models. We present more detailed analysis and evaluation of T-manner in our paper. To be more specific, we take a deep dive into T-manner by analyzing its components and detection performance. In total, we evaluate T-manner on over 1,100 model instances spanning several tasks and datasets. Our code is available on GitHub. Thanks for listening. We welcome any questions.